Okay.
Okay, welcome everybody to this talk of the European Non-Associative Algebra, a seminar, and it's my pleasure to introduce Paola Stefanelli from the University of Salento. She will talk about Płonka sums of the set-theoretic solution of the Yang-Baxter equation. Please, Paola.
Many thanks for the introduction. First of all, I'd like to thank the organizers for inviting me to give a talk in this series of online seminars, this European Non-Associative Algebra seminar. So the main goal of this presentation is to illustrate a connection between a well-known notion in universal algebra, that is Płonka sums of algebras, and another one that is a set theoretical solution of the Yang-Baxter equation. So we can go to the second slide, sorry. Okay, this talk is essentially based on a joint work with Francesco, Catino, and Marzia Mazzotta. But I would like to illustrate these results contained in this paper from another point of view. That is suggested during a conference last year, Loops 23. Indeed, during this conference, I had the talk about strong similarities of cube races, and someone from the audience noted some similarities with Płonka sums that I didn't know before. And in particular, Professor Anna Romanowska sent me an interesting survey on this topic that was written by her and by Jerzy Płonka. And after that, also an anonymous referee of the proceeding I wrote for this conference suggests me to deepen more some aspects related to solutions, so some connection between Płonka sums and solutions. So we can go to the other slide. I would like to introduce something about the quantum Yang-Baxter equation. At first, so the quantum Yang-Baxter equation has roots in statistical mechanics. In particular, it arose from two independent works by Yang and Baxter, the first one in 1967, the other in 1972. The discovery of this equation has led to many applications in different topics. For instance, it led to the foundation of the quantum groups. It contributes to the development of algebra theory, and also it is important in knot theory. And this is only something that I can say about some applications of this equation. There are also quantum computation. More details about this equation are contained, for instance, an interesting book by Lambda and Radford of 1997, Introduction to the Quantum Yang-Baxter Equation and Quantum Groups, an algebraic, where it suggests an algebraic approach. But in this talk, I will focus on a subclass of solutions of the Yang-Baxter equation that is named set-theoretic solutions. This class of solutions at first appeared in the Greenfield paper of 1992. So what is a theoretical solution of the Yang-Baxter equation is if we have an empty set S, a map R from the Cartesian product S times S into itself is a solution if it satisfies the Braid equation, that is this identity. I'd like to underline that in this paper, Greenfield only wrote that maybe it could be interesting studying these solutions, but after that, a lot of mathematicians drew their attention to this interesting topic. And so they started to deal with this challenging problem of determining, classifying all set theoretical solutions of the Yang-Baxter equation. a large number of works related to this topic has been produced in the last year. I have not time to speak so much about all these works, but for sure, these 4 papers can be considered some milestones in about this topic. This of Edingos, Kleder, and Solovev of 1999. This other 2 of Gatevanova and Majid, Gatevanova and Vandenberg, and this other one of Lu, Yang, and Su of 2000. So let me give some definition to fixed notation and terminology about solution. Hereafter, we call simply solution any theoretic solution of the Yang-Baxter equation. And if we write R by using to map lambda A arrow B from S to S, as in this slide, we can say that solution R is left non-degenerate if lambda A is bijective for every A, right non-degenerate if rho B is bijective for every B, non-degenerate if R is both left and right non-degenerate. And also we can say that R is involutive or idempotent if the square of R is equal to the identity or to R itself respectively. Just to give you an idea, the identity map is involutive, idempotent, and degenerate. The twist map, that is the map that changes the order of any pair AB into BA, is an involutive and non-degenerate solution. So we obtain also other example by looking at this other family of solution that Drinfeld called Lupacescu solution, that are these kind of maps R that are defined by using simply to map F and G from S to S that commute. And in particular, R is left non-degenerate if and only if F is bijective, and is right non-degenerate if and only if G is bijective. When these maps F and G are bijective, in particular, these solutions are also known as permutation solution. R is involutive if and only if F and G are bijective, and in particular, G coincides with the inverse of F. Other example can be obtained by considering, by fixing an element K in S. And so if we consider G equal to F equal to the constant map equal to the map of constant value K, we obtain an easy instance of degenerate and idempotent solution. So there are, as I said, there are many works about this topic, and also a lot of mathematicians approach to the problem of finding solution from different points of view, and also by studying different algebraic structures. And I'd like to underline that in 2007, Rumpf traced novel research direction in the study of solutions because he found an interesting connection between radical ring and solutions. I recall briefly that if we have a ring and we consider the circle operation, like that is defined in this way, that is known as a joint operation, the joint operation of R. In general, we have that the structure R circle is monoid, having the same identity 0 of the additive structure. And when R circle is a group, R is said to be a Jacobson radical ring. And a Jacobson radical ring gives rise to a solution R that is in particular non-degenerate and is involutive. But there is another structure, that are basis structures that are interconnected with the involving non-degenerate solution. And indeed, introduce this structure for this relation for studying exactly involutive non-degenerate solution, but even more generally, non-degenerate bijective solution can be obtained through the structure of skew brace. So I will give you the more general definition of skew brace that first appeared in the paper by Guardiani and Vendramin of 2017. So what is a skew brace? A triple B plus circle is said to be a skew brace if B plus and B circle are groups satisfying this kind of distributivity law that we can name skew brace distributivity law. In general, B plus is not an abelian group. When B plus is abelian, then we have a structure of brace, the original structure introduced, the structure that was originally introduced by Rump in this abelian version. And I would like also to underline that this is not exactly the definition that we can see in the paper written by Rump in 2007. This is a formulation provided by Sedoye Spersokoniski later. So we have to note that the groups B plus and B circle have the same identity that we denote by 0. And group give rise to each example of skew brace. Indeed, if we have a group B plus, this triple B plus plus is easily an easy instance of skew brace that is called trivial skew brace. In general, if B plus is not abelian, we obtain also another structure, an easy instance of skew brace B plus, and as a circle operation, the opposite of this plus operation, that is called almost trivial skew brace. In general, this is another structure that is not isomorphic to the first one. Jacob's brace can be considered in the generalization of Jacobson radical ring because if we consider Jacob's radical ring, then exactly the triple R plus circle is a brace. On the other hand, any commutative brace is a Jacobson radical ring. Indeed, if we have a structure B plus circle of a brace, where circle is commutative, we can define this dot operation as one can expect, and we obtain that B plus dot is a Jacobson radical ring. So, as I said, skew braces allow for obtaining non-degenerate bijective solution. Indeed, we can define this map RB that now we can write in this way, where a to the minus denotes the inverse of a with respect to the circle operation. And more specifically, we have that RB is involutive if and only if the additive structure is abelian. That means that B is a brace. A nice result provided by Smutkowicz and Rabin is this order. In the finite case, the solution associated with a skew brace satisfies this relation. That means that the solution is of even order to n, where in particular n is the exponent of the additive quotient group of B modulo its center. So it's clear that if B is abelian, if B plus is abelian, n is equal to 1, and so the solution is involutive. So these results give the idea that all structural properties on skew braces influence the behavior of solutions. As I said, the solution associated with skew brace is bijective. What about the inverse? Well, if B plus circle is a skew brace, we can consider another structure of skew brace that has the same underlying set B, the same circle operation of the fixed brace B plus circle, and as addition, the opposite of the sum. This is called the opposite skew brace of B plus circle. And Koch and Truman show that the solution associated to this opposite skew brace coincides exactly with the inverse of the solution associated to the skew brace B. So after this paper of Rump, of Guarnieri and Ramin, this structure of skew brace were profusely investigated also in their generalization by considering different structure associated to this kind of skew brace structure. So at first, as I said, we have this generalization of radical ring braces introduced by Rump. I'd like to also mention that in 2009, Catino and Rizzo introduced another structure, an independent way from RUMP, that they called radical circle algebras, that are essentially F-braces in the current terminology. That means, or I say only some details, that are braces that have a vector space as underlying additive structure. And they study this structure for another, answer to another open problem, that is finding regular subgroups of a defined group of a vector space. So later we can find these skew braces introduced and started by Guarneri Vendramin. And also in the same year, Catino, Colazzo, and myself introduced another structure that is the semi-braces. This structure, in such sense, is similar to skew brace. The additive structure is a left-cancellative semigroup, and also they provide left non-degenerate solutions to the Yang-Baxter equation. Later, Jespers van Antwerpen studied another structure of semi-brace, where they consider simply a semigroup as an additive structure and show that under some assumptions, this structure produces more arbitrary solutions. Again, we can later we can find the other structure, the inverse semi-braces, generalized semi-braces, where we involved other structure of semigroups, and also study when this structure produces a solution. Then we can find also weak braces, dual weak braces. Sorry if this slide is not exhaustive about this structure cross-related to skew braces. I only mention also these other recent structures that are near braces introduced by Doko Ribowowicz, where they essentially consider two structural groups having different identity, and they always produce bijective non-degenerate solution. We have also these other skew breakouts introduced by Martin Lyons and Truman, but I don't have time to explain more about this structure, so I will focus on dual weak braces and, as I said, their connection with Płonka sums. So I would like to say something about Płonka sums. This is also the title of my slides. Płonka sums is one of the most significant methods of composition in universal algebra that arose in the pioneering work by Jerzy Płonka in 1967. It was further investigated by the same author in some years later, and at first it appeared under the name of sum of a direct system of algebras or sum of a semi-lattice ordered system of algebras. More details are contained in the survey I mentioned at the beginning of the presentation, written by Płonka and Romanowska of 1992. So to define Płonka sums, I first recall some notion. For an omega algebra or algebra of type omega, we mean any pair A omega with a set, and the omega a set of operation symbols. This operation can be of different arity, so we can define also a notion of omega homomorphism if we have two algebras of the same type omega, A omega and B omega. A map phi from A to B is an omega homomorphism between A and B if it satisfies this identity, that is a generalization of the well-known homomorphism between two structures endowed with binary operations, essentially. If phi is bijective, then phi is also said to be an omega isomorphism. Just a remark, an example. It's clear that any group can be considered as an algebra with a binary operation, but it can be considered also as an algebra, an omega algebra, where omega consists of three operations of different arity, the dot operation, that it is the group operation, so it is of variety 2, the inverse operation that is of variety 1, and the identity that is of variety 0. Moreover, any group homomorphism is clearly an omega homomorphism. So to define Płonka sums of algebras, we need to introduce some ingredients. We need some ingredients. The first one is the lower semilattice Y. Then we need the family of disjoint omega algebras that are indexed by the semilattice Y containing non-nullary operations. As written by Płonka, this is not exactly a serious assumption on our family of omega algebras, because it can be replaced by other assumption, but we accept these for now. For all alpha and beta in Y, such that alpha is greater than beta, we can consider a map phi alpha beta from A alpha to A beta that is an omega homomorphism, such that phi alpha alpha is exactly the identity on A alpha for every alpha in Y. And we have also this other rule on the composition of this omega homomorphism. Indeed, if alpha is greater than beta and beta is greater than gamma, then the composition phi alpha beta phi beta gamma is equal to E phi alpha gamma. Then this system, Y alpha phi alpha beta, is named direct system of algebras A alpha indexed by Y. In this way, we can define a new omega algebras on the disjoint union of these omega algebras A alpha. In this way, if we have in omega an n-ary operation, we can project any element, and we fix an element A alpha 1, A alpha n in A alpha 1, A alpha n respectively. We can project this element into A gamma, where gamma is the minimum between alpha 1, alpha 2, alpha n, and then we compute these images by using the n-ary operation on A gamma. This algebra is called Płonka sum of algebras A alpha omega. To be more clear, I want to look at the diagram in the slide. For instance, if we have a ternary operation in our algebra, in our set of omega, and so each algebras, for instance, by considering a semilattice that is a chain, and we have these algebras A alpha, A beta, A gamma. So if we want to define a new ternary operation on A, we exactly project A alpha into A gamma, because gamma is the minimum between alpha, beta, gamma. And we project also A beta in A gamma. A gamma is fixed by phi gamma gamma, that is the identity. And then we compute this product by using the ternary operation A gamma. This is just to give an idea, to be more clear if we want to use more concretely this definition. So some observation. The semilattice Y is endowed in a natural way of an omega algebra structure. Indeed, we can define this n-ary operation, omega alpha 1 alpha n, simply by setting this equal to alpha 1, the minimum between alpha 1, alpha 2, alpha n, when n is greater than 2. And if we have a unary operation, we can define omega alpha equal to alpha. This omega algebra is called omega semilattice of Y, and it is important to note that there exists an homomorphism between the omega algebra A omega, the Płonka sum A omega, and this omega semilattice on Y, that is given by this map P, defined by P alpha equal to alpha, that is called projection, that has this restriction on this subalgebra A alpha omega that are called Płonka fibers. These other maps, phi alpha beta, are called Płonka homomorphisms. So I want to focus on some applications of Płonka sums of algebras, and I'd like to mention that historically, first instances of Płonka sums appeared in literature in a paper of Alfred Obstitel Clifford, this paper of 1941, so more or less 20 years earlier before the Płonka papers, the first Płonka papers on Płonka sums. And these constructions of semigroups were named strong semilattices of semigroups. And I would like also to underline that Płonka sums are also essentially was born by looking at this paper of written by Clifford. Over the years, these Płonka sums turned out to have many applications in different algebraic theories, such as semigroup theory, semi-ring theory. Recently, it was also applied to direct system of algebras with involution, and it was also surprisingly connected to logic, and we can refer to the introduction of this paper by Bonzio. Other new applications can be found in other topics that are far from algebra, for instance, from computer science. So what about Yang-Baxter equation? What are the applications of Płonka sums to Yang-Baxter equation? To answer this question, we can give a look to other structures related to the Yang-Baxter equation that are Dirac structures. So if S is a set, and we write a map Rs from the Cartesian product of S times S into S times S, and we write R by using two maps lambda A rho B, as I said before, for solutions. We can define in an easy way two binary operation dot star, A dot B equal to lambda A B, and A star B equal to rho B A. So it is an easy computation. RS is solution if and only if these three identities, Y1, Y2, Y3, are satisfied. That these identities correspond exactly to the Braid equation. And one can see that RS is left non-degenerate if and only if S dot is a left quasi-group. That means that the left multiplication lambda A is bijective for every A. RS is right non-degenerate if and only if S star is a right quasi-group. That means the right multiplication is bijective now by using the other operation star. And if the solution RS is bijective and non-degenerate, the structure S dot star is commonly named Dirac, as one can see, for instance, in these two papers by Stanowski and by Jedrzejczyk, Plitowska, Zamowska, Zlenio of 2019 and 2006, respectively. So we call weak by shelf any structure S dot star satisfying only the conditions Y1, Y2, Y3, without any other assumption on the involved operations, as well as on the map RS. Moreover, we say that RS is the solution associated to this structure S dot star. We call by shelf any weak by shelf S dot star such that the associated solution RS is left or right non-degenerate. These names are justified by the other known structures that are shelf structures. So what is a shelf? A structure S dot is a shelf if and only if it satisfies this identity that is the self-distributivity law of this operation. In this way, if we simply set A star B equal to A, we obtain a structure of a bishelf. But how to obtain in an easy way a shelf, and so by shelf, for instance, we can look at groups. If we have a group and we consider as dot operation the conjugation of B by the element A, we set A dot B in this way, then S dot is a shelf. And I'd like also to recall that this kind of shelf is connected to another family of solutions that are named bank of solutions, also using the terminology that one can find in the Driffer's paper. Another example, if we have a monoid with identity 1, a monoid S dot, and we set A star B equal to 1 for all A, B in S, we obtain a structural weak by shelf. This is only a weak by shelf if, in particular, the monoid is a group. Of course, we obtain a structure of by shelf. So, what is how to connect? What is the key connection between Płonka sums and the Yang-Baxter equation? This is explained essentially in a paper by Ledwicka, Klitowska, Zamoska, and Znego. Indeed, they observed that any left quasi-group can be regarded as an algebra and with two binary operations, dot and this left slash, that satisfy these two identity. In a similar way, right quasi-group, S star, are algebra with two binary operations satisfying this other similar identity. And as a consequence, natural consequence, biracs can be considered as algebras with four binary operations. In the same way, Bashev and their subclasses can be regarded as algebras of three and with three binary operations. It depends if they are associated to a left or a right non-degenerate solution. More in general, weak by Sheff and their subclasses can be regarded as algebras S dot star, because we don't know any other particular properties on the solution R. So, if we consider a direct system of weak by Sheffs S alpha, indexed by a lower semilattice Y, the Płonka sum of these weak by Sheffs is a weak by Sheff. So we obtain a new weak by Sheff on the disjoint union of these weak by Sheffs S alpha. And since we can equivalently refer to an arbitrary solution RS on S or to a weak by Sheff structure having the same underlying set S, this theorem shows the auto-determined Płonka solution as Płonka sums of solutions, because as I said, Płonka solutions involves algebras. So this is a way for defining a Płonka sums of solutions in a more direct way. And this theorem is essentially equivalent to another, this construction of solution is equivalent to the strong semilattices of solution introduced by Catino, Colazzo, and myself in 2021, where we essentially construct solution by considering a semilattice Y, family of solutions that are defined on these joint sets X alpha. So by considering the map phi alpha beta from X alpha to X beta whenever alpha is greater than beta, then define this map R essentially by considering the solution R alpha on these sets X alpha. We project any element A of X alpha into the set X alpha beta. Here alpha beta is exactly the minimum between alpha beta. We project any element B of X beta again into the minimum, into the set indexed by the minimum between alpha and beta, and then we apply the map R alpha beta, that is the solution on X alpha beta. And we obtain that if the following conditions, phi conditions, are satisfied, then R is a solution on X that we call strong semilattice of solutions R alpha. But I say that this is equivalent to Płonka sums of solutions essentially for this reason. If we have two weak Bashevs, and we have a map F from S to T, then F is a weak Bashev homomorphism if and only if this identity holds. So F times F Rs is equal to RT F times F, where Rs and RT are the solutions associated to S and T respectively. So these maps phi alpha beta are exactly the Płonka sums of the previous construction. So this is the key connection between these two constructions. But How can systematically obtain solutions by using Płonka sum technique? As I have already mentioned, a special case of Płonka sums was dealt with in semigroup theory. In particular, Płonka sums are useful for describing Clifford semigroups, and dual weak braces can be obtained to obtain our goal. So let me introduce some other definition on semigroups. A semigroup is said to be inverse if for each A in S there exists a unique element A to the minus satisfying these two identity. Such an element A to the minus is called the inverse of A. In particular, one can find more details about inverse semigroups in a book of Petrich of 1984. It's clear that any group is an inverse semigroup, and that one can show that the inverse of any element A satisfies properties that are well known in groups. For instance, the inverse A to the minus of the A to the minus is the element A itself. If we compute the inverse of the product AB, this is equal to by B to the minus A to the minus. If we have an inverse semigroup between, if we have an homomorphism between two inverse semigroups, the image Fa to the minus is the inverse of Fa. A central role are played by the sets of idempotents that are exactly the element of this shape A to the minus. In particular, idempotents commute each other. So an inverse semigroup S is a Clifford semigroup if it has central idempotents. That means that idempotents, of course, it means that idempotents commute with all the elements in the semigroup S. And we have this description of Clifford semigroup. If we consider a direct system of group G alpha, the Płonka sum of the group G alpha is a Clifford semigroup. But on the other hand, if we consider a Clifford semigroup, we can find a family of disjoint groups G alpha indexed by of a certain similarity Y, so that this Clifford can be realized as the Płonka sums of groups. And these results are essentially contained in the paper by Clifford. It is also illustrated by the book of Petrich and also in this survey of Płonka and Romanowska. And in semigroup theory, it is more known as strong similarities of groups G alpha. If we look at this description of Clifford semigroups as Płonka sum, I have to underline that each group is considered as an algebra with only one binary operation. The set of idempotents S is isomorphic to Y, and S is a group if and only if the cardinality of Y is equal to 1. So what is a weak brace? A triple S plus circle is said to be a weak brace if S plus and S circle are inverse semigroup that satisfy these two identities. The first one is exactly the skew brace distributivity law. The other identity, where we involve the inverses of S plus and S circle, say us that in any weak brace, the idempotence of the additive structure coincide with the idempotence of the multiplicative structure. So we can simply refer to the idempotence of a weak brace. And as a consequence, if the idempotence, the set of idempotents has cardinality 1, then S plus circle is a skew brace. So skew braces are special instances of weak braces. And if we fix a Clifford semigroup, we can obtain easy instance of weak braces that we call trivial and also trivial weak brace. So we have also this property that involve any idempotent E and any element of S. The sum E plus A is equal to the multiplication E circle A. In particular, ES is a trivial weak brace contained in S. And this is a key property that allows us to show that any weak brace produces a solution. Moreover, this solution has a behavior close to be bijective. Indeed, if we consider the opposite skew brace, and it makes sense to consider this structure, of course, we obtain that RS satisfy this three identities together with the solution associated with the opposite weak brace. That essentially means that RS is completely regular element into the maps from S times S into itself. This sense these solutions are close to being bijective. And if we look at the structure of a weak brace, we have that S plus is exactly Clifford semigroup. In general, the multiplicative structure of a weak brace is not a Clifford semigroup. And we can obtain easy instance of this type essentially by considering the semi-direct product of the Clifford semigroups that in general is not a Clifford semigroup. And we have this easy example essentially by looking at trivial weak braces and by looking at simple example of Clifford semigroups. So we also, but on the other hand, also we have several instances of weak braces such that the multiplicative structure is a Clifford semigroup. We call such weak braces dual weak braces. And if we look at dual weak braces, we can say more about the solution associated to S plus circle, because we have that the maps lambda A and rho A satisfies these three identities respectively, and that says us that lambda A, rho A are completely regular elements into the map from S into S. So in this sense, they are close to be bijective, and so RS is close to being non-degenerate. So if we consider direct system of skew brace, the alpha indexed by Y, we obtain a new structure by defining the circle operation as we already seen for Płonka sums of algebras, that is a dual weak brace. This is a result provided by Catino, Mazzotta, and myself this year. And I show this now. I'm showing this result in this revised version by using the Płonka sum. Conversely, any dual weak brace is a Płonka sum of skew braces, and this is obtained exactly by looking at again at the special properties of the idempotence of a weak brace structure. So it's clear that it's important finding all skew brace homomorphisms for constructing dual weak braces. And it's not surprising that also this problem emerged in literature for other reasons. In particular, we can see that Sedo and Vendramin posed the problem of computing the automorphism groups of skew braces of site P to the N. Zenuts, Pujic, Smuktonovic, and Zenuts use some description of certain automorphism of skew braces for describing, for instance, FB braces of cardinality P4 with certain properties. And also there is another paper by Latiria Dav where the authors focus on skew braces automorphism for developing more general homological, cohomological aspect related to skew braces. This is only to mention why it is important finding these maps. And now, if we come back again to the solution associated to a weak brace, we have that the solution associated to any dual weak brace is a strong similarity of solution R alpha associated to each skew brace B alpha. Or equivalently, the solution associated to S, to a dual weak brace S, is the Płonka sum of a family of bijective and non-degenerate solutions, since they are associated exactly to skew braces B alpha. And what about the weak by shelf obtained this way? So if we consider this family of solutions associated to the alpha, it's clear that we are considering Biracs, so this structure with on the alpha with these four operations, and consistently the weak by shelf obtained by using the Płonka sums of solutions is again, and it should be in this way, an algebra of this type with 4 binary operations, but in this case, this weak Bayes chef satisfies weaker identities with respect to barracks that are exactly these 4 identities. Just to conclude, we also have special properties on the solution associated to finite dual weak brace. Indeed, we can show that the period of this solution R is 2k plus 1, where 2k is the least common multiple of the whole period of this map R alpha. And also we can obtain cubic solutions that are these solutions are satisfying this identity, the cube of R is equal to R. In particular, we have that the solution associated to a finite dual weak brace is cubic if and only if each solution R alpha is involutive. That means each cube brace B alpha is exactly a brace. This is only just a final observation. So I thank you for your attention and sorry for the problem at the beginning of this presentation.
Thank you, Paola, for the talk. So are there any questions? Comments? If not, I have a question for the speaker. Which is the advantage of looking at this problem of constructing solution using this Płonka sum compared to semi-lattices?
It is the same of constructing solution by using the strong semi-lattice of solutions. This is another way to see that construction. But on the other hand, I believe that also the Płonka sums of algebras, essentially of Bayrak, can give other construction such sense. But I have to look more deeply about this. But essentially, it is another way to see the strong semi-lattices of solutions.
Okay, thank you. Other questions, comments? If not, let's thank the speaker again.
Thank you.
I can stop sharing, I believe.
Thanks, Ilaria, for sharing my presentation.
Okay, that's okay. I believe that the next meeting is again on Monday.
Yes, at the same time. Okay. Bye.
Bye, thank you very much.